record. Okay. 2, 1. Okay. So this is the end of our member AB. So let's move on to member BC. Okay. Now this is member BC. You know what? Let's that first member BC like this. Okay, now you just need to know that member BC, there's a joint at B and joint at C. So joint B will have to take the forces from member AB by the end of this joint. You see, that's the location. So now you have the clockwise moment at B. You need to have the counterclockwise moment equal to 3200 kilogram meter at B on member BC as well. So this will have to be 3200 kilogram meter. Okay. So next is the vertical force or the axial force on member AB, 3200 over 6. This one is downward, so you're going to have that upward here. 3200 over 6. Okay, and then the last one, remember AB, you have 800 horizontal force, which is a shear on member AB going to the left. So this 800 is going to go to the right on member BC. And it becomes the axial force on member BC instead. Okay, so now because this is the force on B, okay, on the NB of member BC. So before I proceed, I'd like to show you one thing, that is member BC is quite easy in this case because we don't have any force acting on the member itself. So to complete this free body diagram is rather easy, but it's not always like this. Okay. So all right, maybe I should do this. Sorry, such a bad line. Okay, so again, take take sigma fx equal to 0. You know right away that this has to be 800 by inspection again. And likewise, this has to be, oops, ooh, see that? Okay, it has to be downward, 3200 over 6, again by inspection. Okay, so now what about a moment? Okay, you can easily take a moment at C here. Sigma MC equal to 0. So you see, we now have, when you take moment at C, you have 3200 as a moment. And let's say it's counterclockwise. I don't mind the sign very much. Let's say the moment is positive, but you also have this shear minus 3200 over 6. Because this one goes in the clockwise direction, the moment itself goes counterclockwise, right? So they have a different sign. Which one is positive, it doesn't matter for me. And this moment arm is the length of the member, which is 6. You see that? 6 meters from this, right? That's 6 meters. So you see, naturally, plus mc equal to 0. Let's use the green. So this Oh, forgot that. It has to be multiplied by the moment arm, which incidentally is 6, right? No, let me erase this. It's getting messy. Multiplied by the moment arm is 6. Then plus MC equal to 0. So look what happens here. So they are equal, right? So that means MC is equal to 0. Wow. Is that possible? It is possible because, let's say, you know, I'm gonna, can I, no. Because when you look at the free body diagram of, let's hope that I have enough, okay? Member CD. Here is a roller. And when you look at member CD, you have the downward reaction of 3200 over 6 there. $3,200 over 6. So by inspection, you know that this better be 3,200 over 6 as well. There is no horizontal reaction here, right? So if you are going to have some moment at this location, if you are going to have moment here, what is there to balance this moment? Because axial force cannot produce moment, right? So if you are going to have a moment at joint C, you better have horizontal force at D so that you have a chance to balance this moment. So when you know that there is no horizontal reaction here, it's impossible for you to have moment at C. So it's only correct that when you take the moment here and then sigma mz will give you moment at C equal to 0. In this case, if you have mz not equal to 0, you know right away that you are wrong. Just take a look at the free body diagram of this member alone. You see, that is why I kind of prefer you to draw the support condition on your free body diagram rather than the force. Because if you draw the support here, you will see right away that this is your free body diagram. And you have only this. You cannot have the horizontal force here. No, you can't. Meaning this column cannot carry any moment. We call this lean column. It only leans onto something. So when you have a support condition like this, you would know right away that there is no chance that you can have moment at C. Any question? Okay, guys. So because of this, now you see that right here for member CD, that is the complete free body diagram. It's just the axial force. So this is the lean column, pure column, no moment, no shear whatsoever. So where is the 800 gone? Now, to see the 800 gone, you need to draw the free body diagram of joint C. That's why we need the free body diagram of the joint now. So this is your C here. So when you look at joint C, you know, you have 800 that must go to the right. You see, because this one on member BC here is going to the left. So to balance that, it has to go to the right. And then you have the downward force, 3200 over 6 down. So this is up. So to balance that, this has to be down. 3200 over 6. So if this is down, it becomes the upward force at this member, you see? So that, voila, it's complete. Everything is correct. And this 800 force is in fact balanced by this one, which is, let me erase this. C and D. This is your external applied force at that particular location, right? Which you must include in your free body diagram. Where could it go, right? It's there. So here is your external applied force equal to 800. So when you look at the free body diagram of this joint, it is perfectly complete. So the 800 is gone because this is equal and opposite, this is equal and opposite, so there is no horizontal force on this location, on another end of your joint. So no horizontal force coming onto member CD, because if you look at the free body diagram of member CD, you will see right away that you cannot have the force perpendicular to the member. If there is the presence of the force here, you know right away that your member CD will never be under equilibrium. It can't take any shear because it is a roller support in the end. Okay? Is there any question? Are we crystal clear? Hope so. Okay.
Yes.
Yes. What do you mean? Yes. Yes, no question. Or no, no question.
No question.
No question. Okay. Yeah, English is supposed to say no. Okay. All right. So anyway, we have a job to complete our shear force and bending moment diagram. So I hope you don't mind. It's in the video anyway, and I can do it again here. I think I have enough space. Another $1 million question doing this is that on which side should I draw my yes, Nakarin. Nakarin.
อ๋อผมกดผิดครับ
Ah, man. Anyway, it happens. Okay.
Sir, can I ask you one more question?
Please, anytime. Please go ahead.
How about if we start to consider at member CD? Is it the same with this question?
It is because in fact you can start your free body diagram, you can start your work anywhere you want, anywhere you wish, anywhere that you think it will make your life easiest. In fact, I would myself start from CD because it's easier. But this frame is easy enough to start from anywhere except BC, right? That would be silly. Anyway, yes, the answer is, of course you can. And the answer would be the same because, mark my words here, ladies and gentlemen, third year students, in your elastic world, one loading condition can have only one equilibrium condition. So that means you have this one frame, you have this load, you can have only one equilibrium. There cannot be the second equilibrium. So to put that straightforward, it means that it doesn't matter where you start, your answer should be the same. Okay. The next $1 million question is, when you are going to draw the bending moment diagram, on which side you should draw your moment diagram. So I bet not many of you have noticed this from your days of statics. So let me go to the lecture and try to emphasize this. Let's say you have, how come I use this page so quickly? Anyway, say I have a simple beam. I put the load here. This is my bending moment diagram, correct? Like that. If I have a cantilever beam, my moment diagram will certainly look like this, right? So, can you tell me how we draw bending moment diagram? Anyone except senior? But maybe if senior cannot answer this question, I think I'm going to go back and take one grade off your structural analysis number 2. How's that? Come on, anyone knows? Okay, that's not unusual because this is like a little bit more advanced question, so it's okay if you don't know the answer. Where is the compression on this beam? Top or bottom? This beam. Where's compression?
Top.
Top, right? And where's your bending moment diagram? It's on top, right? Because this is your zero line. What about this beam? Where is your compression? Top or bottom? Bottom, right? So for this beam, you see, naturally, your bending moment diagram is down the zero line now. That is because we, in this country, tend to draw bending moment diagram on compression side of the member. I emphasize we, draw bending moment diagram on compression side. So now you guys need to, see things better because this is a simple beam. So it bends like this. That is your positive curvature. So it's compression on top. And this also associated with the positive bending moment diagram. So we call it positive curvature as well. And it also, is in accordance with your sign convention, positive moment, you see? So this goes like this. So this is your negative sign convention for your bending moment diagram, right? Which is exactly this curvature. But ladies and gentlemen, I'm going to tell you right now that not every country on this earth draw bending moment diagram on compression side. The people with the imperial system, US of A, for example, they draw bending moment diagram on tension side. So with a beam like this, if you go to the US, they draw bending moment diagram like this. And for this, they draw it like that. Okay. Now, I was, say, unfairly mocked by my advisor that, you guys draw a bending moment diagram on compression side, blah, 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 and so and so. So it's, it's unfair a little bit, but they do draw on the tension side. The benefit of drawing the bending moment diagram on tension side is that this will reflect how your beam is going to deflect under load. Okay, so it gives the deflected shape better, or like this as well. But you know, we are in this country, so I suppose we draw it on the compression side as usual. So when we come back and look at this member, where is compression, left or right? Now you guys need to, when you see the moment, you must feel the structure right away. You just, okay, this is clockwise, this is counterclockwise. Let me have 5 minutes to think about this, and then blah, blah, blah. When, you know, engineers must feel stuff like this. Right? What? So when you look at the bending moment here, you see how this moment is going to bend your member, right? So here must be compression. Compression is on this side. So if I redraw this free body diagram here in this line, actually I don't usually draw the axial force diagram. It's not very useful for us because, you know, it's generally constant. So we don't need the diagram, but to be for the sake of completion, okay? Now it is your job to draw the free body diagram of this member. So now if you know that this is where compression is, so your bending moment diagram is going to be on this side, correct? And when you look at this beam, you need to turn it upside down, or maybe you can also draw it like this, you know, I wouldn't mind for your convenience. So that's your 800, 800, and then your moment. It's the same. So like this, that is my shear force diagram. It's a negative value of 800, right? See, because we have a constant shear. Okay. And this shear force diagram, it's constant shear. So your bending moment diagram is going to look like that. Ooh. That is minus 3,200 kilogram meter. Okay. Well, I wouldn't mind the sign convention of the shear very much, because let's say if this is the diagram, if your eyes are here, looking at that from that direction. But if your eyes are on this side, your shear force diagram may look different. Okay. But if we stick to the rules of the bending moment diagram must be on compression side, your bending moment diagram must always look like this. But from the right, your moment looks negative. But if I draw it from the left, and if I start drawing it from this direction, you know, I have the shear, and then the moment will look like a positive value, because if I look at from this direction, the sign convention for moment is like this, which is positive. But if I look from this direction, I see the moment as the negative moment. You see? Is that a question? It's uncomfortable silence, maybe. But let's move on to the next member for the time being. So you see, we are no longer dealing with a simple beam. If you have the end moment, which you can rightly calculate here, and you know the value, you must draw the diagrams to reflect that there's moment there, you know. We don't have a moment diagram like this anymore, because this would mean that your moment at B is 0. Now you have the moment at the joint, so your moment diagram would not be, you know, just like another simple beam anymore. Okay, so move on to member BC now. It's pretty simple for member BC because now you have the positive shear, just like a beam now, 3200 over 6 now instead of 800. And now you have the moment at B. So this compression is down here on this side. And you see, you begin your moment with the value of minus 3200. And you have the positive shear area. It's going to bring this to 0 in the end. So everything will answer themselves, because you have a shear like this. So you have a positive shear area. So this area will be equal to this value. So in the end, your moment becomes 0 at C. All right. Now, for member CD, because we only have the axial force, so there is no shear force diagram nor bending moment diagram. Okay. So keep in mind that you need to complete all the free body diagrams first. If you get this diagram correct, free body diagram, let me use a different color. If you get this diagram correct, free body diagram, if you get this free body diagram correct, that is, you are at the end of level 2 with all correct free body diagram. You need to be able to complete all the free body diagram just to make sure that you have proper equilibrium before you start drawing your shear force and bending moment diagram. And if you have any doubts, you can always refer to this. Okay, so if you get all the free body diagram correct, you will get 40%. That means you just, you know, your nose is here with water. You just pass an F. You just write at the F level. Okay, because you know you are expected to be able to deal with the free body diagram. You've done it so many times, but this is just a free body diagrams of members that form a system. Okay, if you can get that and get your hands on some portion of the shear force diagram, you will begin to get, you know, some points above the threshold. If you complete the shear force diagram and get into bending moment diagram, you're getting beyond 60% now. So again, if you get all the free body diagrams correct, you get some shear force diagram and then some bending moment diagram correct, and then you mess up some shear force diagram, you back down to level 3. Okay, because third year students now, you still cannot draw shear force diagram of members. You know, you must accept that fact. And the points go along with your level. Okay, it's a prerequisite here that you can refer to as well. So is there any question? Sorry, wrong one. Is there any question? If there is any question, I have another one, just you know, for fun. Let's say change the support condition. So we have this instead. Okay. So you see, now I'm going to deal with this. Can I copy this? Okay. No. So yeah, I can only do that. And that's fine. Sorry. All right. That seems to be useful. I can draw it again. That's not that difficult. So anyway, now we have this. I just changed the support condition for fun. You will realize that I have the force here, and then this. You see that if you notice, this portion doesn't do anything. Just might as well remove it, right? So this, with or without this, just the same. This becomes just a burden because there's no force in it, right? So I might as well remove it. Okay. So now here. Now you can see that this one has to be 800, right? And now we don't have any vertical load, so there's no vertical reaction. But still, this 800, they don't, coincide. So I better have the moment. And you see this 800 and that 800, they form the counterclockwise moment. So I'm going to need the clockwise moment here as the reaction, right? It's like that. And how much do we have for the height? I think it's 4 meters, right? Is it?
Yes.
Okay, thank you. Right, no need to go back. So this is 4 meters. So that means easily, this is 800 multiplied by 4, that is 3,200 kilogram meter. So I got my reaction. Since this one is pretty easy, I'm just doing it for fun to let you guys have more experience. So I'm just gonna go over it quickly, but if it's too quickly for your comfort, you can let me know. Let's call this A, B, and C. And just like your friends have asked, you can always begin at BC as well, or you can begin at AB. It doesn't matter really. So for the sake of it, let's begin from BC. So BC does nothing. So you see, you have the external force here. So rightly so, this has to be 800, right? But that's it. Whoa, yeah. Because BC doesn't do anything. It's just there to take the force from C to B. In fact, this is just one cantilever column. All right. So if this is 800, this is 800. And now we have equilibrium because your sigma fx turns into equilibrium right away. And that is your moment. Okay. So I can do this. And can I rotate this? I can only move it, right? No, I can't rotate it. So is there any rotation option here? The lasso thing?
What application do you use?
Good note.
Just tap on your screen.
Choose
I do.
resize option.
Okay. Resize?
Just one tap and resize.
Okay, like that. Thanks a lot for the tip. So, okay, you can do it like this, and now you can draw your shear force diagram and bending moment diagram very easily, right? So this means, thank you for the tip. This means the compression is here, but this, when you look at this from this direction, you know that you have the positive moment. So your shear force diagram, it's down and up. The shear force diagram is like this, positive, right? So it becomes a negative. Shear force diagram, 800, and this negative area will bring your moment from positive 3200 to 0. So this is, sorry for not writing at all, shear force diagram and bending moment diagram. Voila, we're done. Woo. Is there any question? Piece of cake, right? Uncomfortable silence. Guys, okay? Okay. So that's oops, sorry. That is also done with pages to spare. So now we're gonna have we are beginning to have more load, more fun. But okay, this is one in the chat. Yes. What's me? Yes. Okay. Yes. All right. So we're gonna do this, but I suppose because the previous example ends rather nicely, and it's been only 40 minutes. We have 10 minutes before the break. So wouldn't it be a nice time to talk about the factor of safety now, or you think I should keep it at the end?
Maybe it's time.
Maybe. Okay. So maybe. All right. So let's talk about factor of safety. Let's hope that I should be able to end this in 10 minutes. Okay. Generally, let's say a factor of safety is always hidden in the design process. If I am going to design, let's say, a cable car, okay, and then this cable is hanging like this, that moves like that, you know, the cable between the valleys and stuff. You know, the factor of safety involved with the design of this cable, this particular cable that supports everything, is 6, meaning they call it omega, is 6. This generally means that if you have a cable, one cable, that can take the force equal to 1200 kilogram force, you have a material, you know, with everything. You will be allowed to use only 12,000 divided by 6, or 2,000 kilogram force in design. You need to keep 1,000 somewhere safe. You're not going to use it. Why? Because the cable is a very dangerous structure. If it is torn apart, it means that this is free fall, right? So that's why they use factor of safety so high. So if you have a rod that can withstand 12,000 kilogram force, when you design it, you can only use the force equal to 2,000. Okay. Now let's look at this from another perspective. Let's say in cable. Now you know that this is maybe 20,000 kilogram force. You need to find a cable to support. Generally, it means that this is say plainly speaking. So the force that you require must be divided by this. generally we don't use this kind of symbol anymore. Rightly so, we need to use this symbol. Okay, the force of the cable that you're going to use divided by factor of safety should always be greater than the force that you need. Okay, your cable needs to support this much force. So in the end, it is this. So let's say, now you know, let's say if a factor of safety is equal to 6, the same. Now you know your T must be greater than this. All right. Now, if you select the cable that can withstand the force equal to 120,000 kilogram force, your factor of safety is exactly equal to 6, right? But let's say in this calculation, you need to go and find the size of the cable that you're going to use, right? So you know the force that you need, but after the calculation, you realize that the diameter of the cable that you are going to use is something like 1.847 centimeter, for example. Will you go out and find the cable with this exact diameter somewhere so that your factor of safety is 6? They're gonna praise your ancestor for that, right? When you write it down in your drawings that the diameter of the cable is 1.847 centimeter. So we need to be practical. We need to use the size that is truly available. So probably you will end up using the cable with diameter equal to 2 centimeter. You can't choose the size below this number. You need to choose the size bigger than this. So in the end, we design with the factor of safety that is required of us. But when we actually choose the size, here would mean that you generally have factor of safety more than that is required of you, because you can't go below. Or I can say the same as this. Okay, let's look at this, for example. You can see the purlin here. That's a purlin, right? So the design of the purlin may require you to check two things. First is the strength of the purlin must be okay. The second is what we call the serviceability, service plus ability, to make sure that the deflection of the purlin is also acceptable. So generally, this kind of structure would end up, being controlled by serviceability. And in serviceability, you look for the moment of inertia to fight off deflection. So let's say to pass the serviceability, you calculate and you know that you require the moment of inertia equal to 2437.8 centimeter to the power of 4. Now, when you select the section, there's no section with this particular number. So you would have to go for the section with moment of inertia larger than this, right? Common sense. So that means, yes, if you wish to consider the serviceability as a factor of safety, you are now have factor of safety more than what is required of you. You cannot have less. Okay, so that's how it works for factor of safety, but it is always generally included in the calculation. It's hidden somewhere in the strength of your material or strength of your structure. Okay, you will learn more about this in the design classes, such as the RC design or steel design, foundation design, so and so. Okay, So that ends nicely because we still have like 3 minutes left before the break. I'm gonna stop the record now.